travelling those vast distances is next to impossible, especially if you consider a human lifespan, let's just say 70 years. At the maximum speed we could go in 70 years, we're not getting very far. We're not getting even to the closest star.
I can't think of any more human activity than conducting science experiments.
The game I play is a very interesting one. It's imagination in a tight straitjacket.
The beauty of a living thing is not the atoms that go into it, but the way those atoms are put together.
What I always think should be the basis of education is not answers, but questions. We should teach kids how to question.
Welcome to Blab Codes. My name is Hamid Siddiqui. So today on the podcast I had Dr Ain De Horte, who is an astronomer, astrophysicist at the Penrith Observatory at Western Sydney University. He's a really interesting guy to talk to, and in this episode we spoke about a lot of different things, really cool things. His journey into astrophysics and astronomy. We spoke about his research into SETI, so the search for extraterrestrial life. We talked about how we know that the universe is expanding, and what type of evidence we have for that. But also we talked about his research into supernovas. So you may or may not be aware, but we are created from stardust. So when stars explode, a supernova happens. So that's the explosion, and all the guts, all the elements like carbon and nitrogen and iron, all of these burst out from the star, and that's what planets are made out of. That's what we as human beings are made out of. So we spoke about that. I also asked him a bunch of chemistry stuff. Physics stuff, and astronomy stuff, because this is my first time talking to an astronomer, and I thought, okay, I'm just not going to leave any questions behind. If I have any questions, I'm just going to try to get an answer from an expert right here, right now. I really enjoyed my conversation with Dr. Ain. He's a really nice guy, and they also have observatory, or I should say stargazing nights twice a month, so you guys should definitely check that out and book a session, because I know I will, and also don't forget to like our Facebook page, give us a rating and a review. We have a competition, so anyone who gets let me see, I have a shirt here. So if you're listening to this, then I would encourage you to actually watch it on YouTube. But we have a nice Blab Codes shirt. Look at this shit. Look at this. This is cool. And you have Blab Codes written on the back. This is our first shirts that we've created. We're going to create and design some more. So the competition is as follows. So if you can get 5 people to like our Facebook page and type up, essentially comment, give so-and-so a shirt, then you go into the draw of actually winning one of those Blab Codes shirts. But there's another competition at the same time. Whoever gets the most amount of recommendations, so if you get 20 people or 10 people, whatever number it may be, and if yours is the most by the end of, let's say, 2 weeks, so it's the 3rd of September now, so we'll find out on the 17th of September who gets the shirt. But so if the person has the most amount of recommendations and friends going on our Facebook page and saying, give so-and-so a shirt, that's the person who wins. And the person who gets 5 people to recommend recommend them goes in the draw to win a shirt. So if you do both, you never know, you might win 2. Anyway, here's the episode. I really enjoyed my conversation. I hope you guys do too. Get ready to learn some physics shit.
So are you into music as well, or?
Alex is into music. He's a musician. Right. I unfortunately didn't have the luck, or I should say, I wasn't fortunate enough to be born in a musical family. so I never got the chance to develop those skills and get into it. How about you?
Well, likewise. Or it skipped me because my dad could sing, my brother can play guitar,
Wow.
and I'd love to be able to, but I can't.
Yeah, I feel the same. I have friends that are singers and friends that can play instruments,
Yep.
like violinists and guitarists, and I just look at them with so much envy.
Tell me about it.
Because it's so cool. I mean,
Yeah.
you know, one thing that I realized when doing science is that the more you know about how the world works, the more interesting and wonderful it becomes.
Yep.
And so if you understand music, it's just another avenue for you to appreciate
Yep.
how the world works.
Yep.
And I've been robbed of that. So thanks, Mum. Thanks, Dad. So let's start. This is my first time interviewing an astrophysicist, or even talking to people who are in the field of astronomy, cosmology, astrophysics. So I'm very excited, Ain.
Okay.
I'm looking
Well,
for.
I'm not a cosmologist, though.
So tell us what you do.
Okay. Well, what do I do? Well, mostly now I actually run this observatory you're at. And so my job, or as I see it, apart from my teaching, is to take science out to the community, to explain what it is that we do as astrophysicists, and just spark something in the youth. That's mostly what I do at the moment. So,
Was there someone specifically who put a spark in you?
I don't think there was one specific person. There was a few teachers along the way who sort of got me interested, but I think I was just a curious so-and-so from a little age. I mean, I always remember that the first thing I did when I was allowed to go into the city on my own, went to what is now the Powerhouse Museum. When it used to be in its old location, it was called the Museum of Applied Arts and Sciences in those days, and that's the first place I took myself. Because
Really?
I just loved that. I could have hung out at that place all day. Yeah.
Wow, so you were a very curious
Yeah.
child.
Oh yeah, yeah. I used to pull things apart to see how they worked. Sometimes I could get them back together.
Yeah, Alex, in fact, that's funny because I used to do that with electronics all the time and just ruin it. But it was just fun to see, this is the little bits that go into this. Alex, interestingly, he was very much like that, but he would do it to animals.
Right.
And so one time, there's a story he told me. One time he found like a blue-tongued lizard.
Right.
I think that was hit by a car or something. It got hit. And he thought it was dead. So he starts dissecting it. And he opens up the chest cavity and he sees the heart beating.
Oh dear. Yep.
I get to you, man. That sounds like the origins of like Dexter or
Yeah.
some psychopath. You shouldn't go around telling people that story.
No, I never did that, but I was very curious.
And so, how did you feed that curiosity?
How did I feed it? I read quite a bit, mostly popular science stuff. I went to the museum all the time. Whatever science shows there were, I was into them.
Wow.
I used to love watching the Curiosity Show and things like that. I don't know if you've ever heard of that.
No, I haven't.
It was a great Australian TV show from the 70s.
Right. What was it like? Well,
What was it like? It's probably really corny nowadays, but there was two guys and they do all sorts of things, and it was scientifically based. I've seen nothing that sort of compares to it because it never talked down to kids. It was really straight on, and got into some quite heavy stuff for kids. And as I said, never talked down to them. And I also remember Professor Julius Sumser Miller. I don't know if you've ever heard of that. Okay, once again, great. He was, I think he was an actually expat American who was here in Australia and had a TV show, and it was Why Is It So? You really must look up some stuff on YouTube on the
will.
Curiosity Show and Professor Julius Sumser Miller. But I just loved that sort of stuff. I also remembered this when I was in primary school. It was Maroubra Junction public school. There used to be an after-school activity run by I think it was the PNC, so it was the Mothers Group, and it was a science club. And so I used to hang around for that. And it was, it was non-scientists, but trying to spark interest in science in kids. And I already had that interest, but I remember the big wow thing was getting, in those days you had milk bottles, and you had milk delivered.
The glass bottles?
The glass bottles,
Old school, yeah.
And getting the hard-boiled egg into the glass bottle by basically sticking a wick of burning paper into the bottle and then sticking the egg in. As the air is sucked out, then the egg gets drawn into the bottle. But yeah, used to.
So they'll do things like that. That's
crushing cans without touching them.
How do you do that?
Well, you put a little bit of water in the can, you boil it up, and then you put the lid on it, and you just wait till it cools down. And obviously, as it contracts,
I think MythBusters did an episode like that. I think they did it with one of those trucks, the ones that carry petroleum.
Oh, okay.
Yeah, and they did it. They heat it up to, I don't know, like 100 degrees Celsius, right. and then they let it cool down.
Right, that's on steroids, so I can see MythBusters, and they probably blew it up afterwards.
Yeah, I think they blow up everything. Yeah. But that's a cool show.
Yep.
So you were surrounded by, it seems like, an environment of science enthusiasts.
Yes, though I'm the son of immigrants, so we came to Australia when I was 3 years old from Uruguay. My parents had hardly any schooling, and that's what they wanted for us is schooling. And Dad was self-taught. Everything he knew, he effectively taught himself.
Wow.
So he was curious, and I was curious, but I surrounded myself with that sort of stuff. I was always the geek, I wanted to make a robot and all those sorts of things.
That's so cool. So your parents were that's a very similar story to mine. So I came here when I was about 7 or 8 years old from Afghanistan. So we left a place of war, and my parents were very they viewed education as something very important to them. And it's interesting, none of my parents are scientists. My mom was a high school teacher, and my dad used to teach history at university.
Right.
But both of them were very curious, and I think they thought like a scientist. They wanted to learn more, and they were very interested in the human body and how the world works. And I think that kind of seeped into me and got me interested in science.
Yeah.
So, how did you then? You had this fascination with science. How did that develop into a career into science?
In a roundabout way. Well, I actually wanted to join the Air Force before I got into university, but I wanted to go in as a pilot. Nothing else would have done, and I missed out in the first intake. So I came to uni, and the thing that I was best at was physics, because I didn't need to really do a lot of work on that. I was just sort of naturally natural aptitude in that sort of area. I failed biology miserably, and chemistry I was okay at. And so I thought, in the meantime, I'll start doing a science degree. Ended up staying in the science degree. I majored in physics, eventually passed the biology I needed to pass, and then I did my honours, and along the way met some people I really admired and look up to, and I guess that with my undergraduate degree in physics and computing, as it was in those days, I actually did quite a bit of hardware development, and that's sort of led me to astrophysics in an indirect way. One of the lecturers I met along the way, who unfortunately is no longer with us, was Bobby Vale, and she was an astrophysicist, and she took me out to parks when I was in my third year. She was doing some observations and thought, come and have a look at what we do. And at that stage, I thought, no, I don't like astronomy. I like all the gadgets behind the scenes. I'd love all the equipment and so on. So I was more into the engineering side rather than the astronomy side.
Right.
But many years later, I came around and I actually then did my PhD, and I studied supernova remnants. So, I've now gone full circle. And,
Right. That's interesting. So, engineering brought you to astronomy.
Indirectly. I mean, I'm not an engineer.
Right.
As I said, my degree was physics,
But that's what you were
and
interested in.
computing. But no, in the computing, there was a lot of hardware.
Right, okay.
So when I say computing, it wasn't just the programming side; it was the
build it.
microprocessor interfacing, microprocessor hardware, as it were.
Right.
There, so it was at that particular time when everything was going digital, basically. So, I had a knack for designing equipment and building equipment.
Right.
Yeah.
So you said you did an honours. What did you do your honours on?
Well, I did my honours, and this was indirectly astronomy, and that's where some of my early work was in signal processing. I had a board that had been designed by a chap in Harvard. His name was Paul Horowitz, and it was a spectrum analyzer, and it was a new digital technology. It actually used some chips developed by the CSIRO that did fast Fourier transforms. So I built an interface for this board, and I evaluated its use of the board. So that was my honours program. So there was some physics in that, but mostly engineering.
Engineering, okay.
Yeah.
So you've kind of mentioned a couple of things that I think need unpacking.
Yep.
So it was it was a spectrum analyzer. So
Yes.
that's just looking at, for the guys who don't have a physics background or science background, it's just looking at all the colours in the light.
Yeah,
And-
and in this case it wasn't for light, but it could have been. In this case it was for radio signals. So it was attached to a radio telescope, and we were looking at radio frequencies, not at optical frequencies.
Okay.
Yeah.
And you mentioned Fourier transforming.
Yep.
So that's just breaking down the signal into its basic fundamental components.
That's right. Well, it just breaks it up into its spectrum. So if you have a time signal, then you can see what that time signal is, what frequency components make up that particular time signal. So the easiest way to think about it is like getting the white light, passing it through a prism and seeing all of the colours that make up that white light. The colours represent the different frequencies,
Right.
and the intensity is just how much of that particular colour is present. So in this case here, it's a radio signal, and you're breaking it up into its component frequencies and the proportion of each of those component frequencies.
Right. And what would that enable astronomers to do?
Well, in this case, what this board was meant to do was look at narrow band signals. So it's like having a stack of radios all tuned to a slightly different frequency, and seeing just how strong a particular signal is in any of those given frequencies. And it was developed to do a thing called SETI, the Search for Extraterrestrial Intelligence.
Oh.
So it wasn't to do any standard astronomy, because we're usually looking at broader band signals. This was
Narrow band.
narrow band signals, yeah.
Okay, so broader band, those are the frequencies that
Oh, it's
distant from
spread
each
out
other.
over
Spread out.
over many frequencies.
Right.
Instead of having a lot of energy, you just concentrated in one or a few frequencies.
And so when you're looking for extraterrestrial life, why would you focus on a narrow band frequency?
Well, I guess the idea was that we've developed radio, and radio in our case works by putting a lot of energy in a very narrow band of frequencies and transmitting that. So I'm talking about AM radio or FM radio, that sort of thing. And if you want to communicate over very long distances, it's very hard to actually travel those long distances, but it's very simple and cheap to send a radio signal across the galaxy.
Right.
You just need some energy, not a lot of it, and then time, and the signal will travel at what we think is the universal speed limit, the speed of light, basically.
Right.
So if you're looking for if there are other intelligent beings out there that have discovered the same physics we have, then if they want to communicate, maybe they'll do it in the same sort of way. So you're looking for those narrowband signals, and also we don't know anything in nature that creates narrowband signals. Natural processes create those broader band signals, but not the narrowband signals.
Right. So if you do see narrowband signals, then it's a hallmark of potentially
potential. That's the important word. Yeah, potential.
Extraterrestrial life.
Potential. Yeah, either that or we've discovered some new physics. We need to,
Right.
is there something that does naturally produce that? Yeah.
So, what were some? Because I'm interested in because I was a big alien conspiracy theorist.
Right.
I think when I've spoken to my friends, a lot of my science friends came from like a conspiracy background.
Right.
They were like convinced.
X-Files, right?
X-Files, the Illuminati,
Yeah.
you know, all of that. And then I think as they learn about the scientific method, they realize, this is all nonsense.
Yeah.
Or it's potentially really, really probable that it's nonsense. You can't really rule out anything.
Yeah.
But can you tell me more about this search for extraterrestrial life? So was that
Sure.
the only effort that was made, or were there other efforts that were made to actually looking for ET?
Well, I guess this is the only true scientific effort at looking for extraterrestrial intelligence. I guess that we come from the idea that travelling those vast distances is next to impossible, especially if you consider a human lifespan, let's just say 70 years, at the maximum speed we could go in 70 years, we're not getting very far. We're not getting even to the closest star. So,
What is the closest star to us?
well, I guess that was a bit of a slip. The closest star is the sun, but the
Besides the
sort of besides the sun, besides the sun as Proxima Centauri. So
How many light years? Is that?
about 4 light years away. So
Okay.
if you travelled at the speed of light, it would take you 4 years to get there, and 4 years to get back. But there are certain things that happen when you travel at the speed of light.
Yeah.
So by the time you got back, everybody you knew, you would have aged 8 years, but everybody that you've known would have been long dead, and so on, because of the relativistic effects.
Right.
And so on. But we can't travel at the speed of light because we have mass. So unless there's some other ways of moving through time and space that we don't know about at this stage, and there may be, actually physically travelling to the stars is out of the question, which then others visiting us. Well, if they're that advanced, they're not going to be crashing in Roswell
Right.
to have people do autopsies on them.
Right.
Yeah, so, I mean, if they're that advanced, they're either here already, but they're so advanced we just can't detect them because we just don't know enough yet.
Right. Or they haven't even come.
Yeah, exactly. Yeah. Yeah.
But when I think about this, I mean, one thing that convinced me that ET hasn't arrived on Earth is, as you said, the time it would take to go from one star to the other 4 light years. That's assuming you're traveling at the speed of light.
That's right.
That's gonna take ages
Yes.
if you can't do that. So obviously,
Not in one generation anyway.
yeah. So do you think it's more probable that if there is life out there, they'll probably send drones like things that we're doing to Mars?
One thing I hate to do is to try and second guess what if there is an alien another intelligence out there, what they would do, what their motives would be, because all we're doing is sort of projecting our own motives, and whenever we say what they could do, we're sort of thinking of the technology that we know ourselves. So what would they do? I don't know. Would we do? Well, yes, we'd send a drone. Effectively, we've sent a drone. We've got Voyager 1 and 2 that have left the solar system now. So effectively, they're like our first attempts at drones to travel into interstellar space. So what would they do? They might do that. Considering those vast distances, unless they're so far advanced that they do know how to control wormholes, they know how to bend space or whatever. They've discovered physics we haven't discovered. They operate in a different dimension to us or whatever.
Right.
Yeah.
That reminds me. Have you ever watched Expanse?
Expanse. No, I haven't.
Oh, you have to get into
I've got
it.
to, yeah.
It is so
Is
good.
is it on streaming television?
It's on Netflix.
Netflix. Expanse. I'll have to have a look at it. Okay.
Yeah. It's interesting because, you raise a good point. It's if we're going to speculate what alien life is going to be like, most of the time I think we're just going to project what we think is going to be like. And I think there's a famous case. I'm not sure if this was a scientist back in the days or some radical thinker. He was speculating what alien life would be like on a different planet.
Yep.
And he essentially reached the same conclusion that it'd be exactly like us because of... He made
the argument. 2 legs, 2 arms, and 2 eyes, and okay.
So that always that cracked me up. It just shows how limited our imagination can be when we think about alien life. But in The Expanse, I bring that up is because they have this thing called the proto-molecule. Supposedly, this has come from outside of our own solar system,
right?
And what it does, it takes your life force and turns it into a new life force. It's really weird, and I recommend you should watch this.
Okay.
Obviously, it's not entirely based on science,
Yep.
but the physics, actually, the spaceship,
Right.
all of that is based in science. So what they do is when they take off, they keep the acceleration at 1g,
Right.
and then when they get close to their destination, they turn the ship around and decelerate at 1g.
Right.
So you experience gravity throughout the whole time.
Right.
So it's really fascinating, but I brought up because of that alien thing, almost like a contagious, I wouldn't even say bacteria, protomolecule that can take over people's lives or their physiology and their life force and turn it into take over. Like they can manipulate physical laws and that may be possible, considering that if there is a civilization that has that existed a million years or is older than us, then they could potentially develop technologies that may seem magical to us.
Oh, absolutely.
Just like an iPhone would seem magical to someone from 1,000 years ago.
Not even 1,000 years ago, but yes, absolutely.
Yeah.
So anything that advanced would seem like magic.
So in your honors, you worked on this,
Yep.
and then what did you do from there?
I was actually a lecturer, mostly teaching. So it was mostly teaching for a few years, and then
Where did you teach?
I taught at back then it was UW, University of Western Sydney, MacArthur. So mostly teaching in courses related to computing and engineering. So I taught digital communications technology, electronics, some computing, and networking, data communications subjects. So it was mostly teaching, a little bit of research on the side, and I think in the 1997, I got the opportunity to travel to the US, to UC Berkeley, and I collaborated with a team there who is the team who is currently doing the biggest SETI search in the world, and they're actually doing it partly here in Australia, thanks to a Russian billionaire, Yuri Milner, who's funded a project to target a whole bunch of stars, over 1 million stars, with the best technology we have to do a search for extraterrestrial intelligence. So I worked with them for about 8 months, built some equipment with them, bought that back. We used that at the Parkes Radio Telescope, and that was at the Parkes Radio Telescope. It was Southern Serendip until about 2007. And I then, about 2007, started my PhD.
Right.
So I did my PhD, and I did in astrophysics, as I said, looking at supernova remnants.
Okay. Can you tell us a little bit more about that?
Sure. You may wonder why I didn't do a PhD in SETI. Okay,
Right.
But that's sort of got chances of success of fairly small, but it'd be an awesome thesis if you found something. Yeah.
Right.
So, but anyway, an interest I always had was in the life cycle of stars, and particularly at the end of the life cycle. And supernova remnant is what's left over after a star has exploded in a supernova, and the remnant is what enriches the space, and basically what we're made of from
stardust.
Stardust, yeah.
So can you just give us an idea of what the life cycle of a star is?
Sure. So a typical star, like our sun, is probably a second or third generation star. So the very first stars would have been probably just pure hydrogen. That was the first element in the universe, and it's just a collapsed cloud of gas that has become so dense that in the center the forces of gravity pushing all of the molecules together eventually gets hot enough to start nuclear fusion. So the elements will fuse into helium, and then the helium into the heavier elements, and so on, and that starts, if you have enough gas, becomes a star.
Right. And why does it collapse?
Gravity.
Okay.
Like everything, gravity. It pulls everything together.
So as the hydrogen or these gas clouds, as they slowly come closer and closer, the gravity builds up, and the heat builds up, and that provides enough energy for the hydrogen atoms to
fuse together. You have to have enough gas because you need sufficient gravity to produce those high temperatures to get nuclear fusion to start, and you need a whole bunch of balances, because if the cloud is too hot, then the molecules are going to be moving around too much. It's not going to collapse in on itself easily. It's got to be cool enough to collapse, and once they do collapse, you've got to have enough of it to spark off fusion. You've got to have enough gas there, so excuse me, so that when it collapses in, the forces pushing out, there's enough holding it then. So a star is effectively in a balance of forces pushing out and the gravity pulling in. So
the forces pushing out comes from the
from the
fusion.
Radiation and the fusion. That's the radiation pressure that's pushing out, and the gravitational forces pulling everything in. And you've got to have that right balance, and if you get it right, then you'll get a star.
And so as a star ages, does that balance start to change?
Yes. So depending on the size of the star, if it's a large star, a lot of mass, then you're going to burn hotter. And when I say burn, I'm not talking about chemical burning, I'm talking about nuclear reaction fusion. It's going to burn quicker and die younger. So it quickly goes through its life cycle. A star like ours is not that massive, so it sort of burns slowly, has a longer life cycle. But the life cycle means that as the fusion takes place in the center, you're fusing and becoming heavier elements. So it's a bit like an onion. So you get concentric zones where you've fused, the elements have fused, the hydrogens become the helium fuses, and so on. You get all of the heavier elements until a point where you get up to iron at the core, and you can't fuse the iron because you need more energy in to fuse it than you'll have got. So at that point, you stop the fusion process, effectively stops. You've still probably got fusion going on in the outer shells, but it starts to cool down. And depending on the size of the star, if it's a star that's about 3 times the mass of our sun, then you will go off in a supernova when you've run out of fuel, because it basically crushes down on itself so quickly, it gets to a point where it can no longer get any more compact, basically, so and you get a shock wave, and that's when you get the supernova explosion.
So because that energy isn't there to keep it from collapsing, it collapses, and it bounces back, as it were, and that sets up a shock wave, and that's starts the supernova explosion. Okay. That's if you're 3 times the size of our sun. If you're about the size of our sun, what happens is you just get bigger and bigger, because now the gravity can't
hold it together, as it were, and there's no extra fusion going on, and you'll get one of these beautiful things that we call a planetary nebula. So basically, it just slowly cools and disperses out. So it doesn't go off with a big bang. It just
slowly
dissipates.
Just a question. So you said, so shouldn't our sun also collapse, considering that it doesn't have that energy to keep it from collapsing? Why does it get bigger?
No, it will collapse, but the outer shells, there's nothing to hold that. So the outer shells effectively just will come off and be pushed away from the radiation that's on the inside.
I see. So the inside collapses.
Yes. But it won't collapse to the point where it'll cause a supernova explosion. Yeah.
Okay. And so are there stars that are smaller than our sun?
Yes. Yeah, brown dwarfs and things like that. So they're smaller, colder. I guess Jupiter is probably a star that never was, because it just didn't have enough gas to get fusion going. But Jupiter is, one of the gas giants in our solar system. Just not quite enough gas to actually get fusion going in the center.
Okay, this is a dumb question, but what if you send like a nuclear bomb to Jupiter? Could you start off the process?
You possibly could, but I don't know that it's self-sustain, and you'd have to get it right in the right place. That bomb right in the right place to kick it off.
Right. Okay. So you're looking at the remnants of supernovas. So you're looking at the stardust, essentially.
Yeah, you're looking at what's left over. So it's the material that's been ejected from the supernova explosion. So that material goes into the interstellar medium, and it pushes out with that matter, and it sets up that shock wave that makes that shell expand, and that is what's enriching the interstellar medium with the heavier metals and the materials, effectively the stuff that allows us to be made. I mean, we know that the sun must be a second or third generation star, because we're here. The Earth is here. The core of the Earth is iron. So there must have been a star at some point that exploded and created those metals and materials that we are effectively made from, the carbon and so on.
Yeah, and that wouldn't have been possible as a first generation star, because
all that would have been around was hydrogen basically. Yeah.
Huh. So what questions were you trying to answer in your PhD?
Well, just looking at the mechanisms of the enrichment, and looking at how we could try and tell what type of explosion created that particular remnant, because there are different types of supernova, all depending on the energy and sizes of the initial explosion. So a remnant could be thousands of years old. So the original supernova explosion, nobody has actually seen that. So trying to work backwards, it's like trying to get our models more accurate, so that we can then simulate working backwards, try to figure out what was the proto-star, the star that actually created that remnant.
So you're like a crime scene investigator. You're looking at what's left behind by the criminal, and then trying to figure out what happened.
Exactly, yeah.
That's interesting. So each type of supernova would exhibit a different residue or stardust.
Yes, yeah, and it all... many variables there. I mean, like the environment it's exploding into will produce something different. You could have two stars exactly the same size and so on, and they'll go supernova, but the environment they're in, it could be different, and so you'll get a different remnant at the end of that. So, that's another variable there. So it's not like you can just say, oh, well, that particular thing's got this shape, so it must have been this sort of star.
Right.
Well, it depends the environment it's in as well.
Right. That's interesting. So there's a lot of variables there.
There is a hell of a lot of variables, and it's not like most science. Astronomy and astrophysics is not like most sciences where you go in the lab and can test that, because we don't have another universe to play with and vary the variables. Though that's why we use computers. Like we build universes in computer simulations and test those and see how our models hold up, whether we can produce something that resembles what we have in nature. Yeah, what we see in nature.
So besides computer models, how do you actually go and study this?
Well, you make observations.
How?
Okay. In my case, most of the observations I made were radio telescope observations. The remnant of a supernova will produce what's called synchrotron radiation, the shock wave, the material moving in the interstellar material as it hits other gas produces this synchrotron radiation, and that's detectable at radio frequencies. So basically I point radio telescopes at that, make the observations, try to make measurements of the expansion, if there's any detectable expansion of the material, the magnetic fields that are detectable, and so on. So that's how I observe that. And you combine that with other observations, for example, X-ray observations, if there are any optical observations, infrared, all of those. And each of that tells a different story. It's a different part of the physics that created what you can see. And from that, you're piecing together the mechanisms of how they have evolved. And obviously, the more observations we have, we can see which theories are holding true. So the cosmologists or the theoreticians will put out that idea, and we can go and make observations and see if we can find evidence for those.
That specific theory.
Yeah.
That's fascinating. I watch a bunch of astronomy documentaries.
Yep, so did I.
Yeah. I'm fascinated by it, and it's a shame because when I was in high school, I think maths and physics scared me just because of the mathematics.
Yeah, well, I believe it or not, I was physics, but I used not hate maths, but I wasn't that great at maths. I think because I couldn't see an application for it. But apart from the obvious thing, going to the shops and making sure you get the right change. But whereas in physics, I really saw, well, this is, maths is my toolkit, to work these things out. So I guess that's where my appreciation for maths came from.
You were obviously much wiser than I was in high school.
Oh, no, I don't think so. No. I was a bit of a mischievous kid. Oh, yeah.
What did
blowing things up and getting...
Really?
Oh, yeah. Come on, that's where the fun is in science, if you can't make something blow up. So now I'm studying the biggest explosions in the universe.
Right. That's so funny. I can't blow anything up. I'll get arrested.
We will nowadays, yeah.
Nowadays.
But there's some of the things I used to get away with in those days, yeah.
That's fascinating. But you're right. Once you understand the application, and I think I realized how important mathematics was in understanding how the universe works, not only at a large scale, but at a small scale.
Yeah.
I did a project where I had to model the tongue movement of singers.
Yep.
And I had to use quadratic equations. And I hadn't used quadratic equations since high school. And I thought, man, if they approached it like this, where they showed me the utility of mathematics, I would have been way into it.
This is where it's very important to have very good maths teachers and science teachers as well. But maths teachers, I think in particular, to have very good maths teachers is very, very important. Because, yes, in my teaching career, I found lots of students who are scared of maths. And that's a bad place to be scared of it, okay? You don't have to be the best at it, but don't be scared of it. It's really a very useful tool. And I think that fear comes from, unfortunately, teachers who are also not very good at it because that's not their primary, and they have to teach it because there isn't enough maths teachers out there. Right. So good maths teachers are very, very important.
Yeah, good teachers in general can change the trajectory of your life.
That's right.
I was fortunate enough that I had really good science teachers. Otherwise, I would have been a historian or something. A couple of questions from these science documentaries, these astronomy documentaries. So, one of the reasons why scientists know that the universe is expanding, and again, like you were saying, you could look at make all these observations and
Yep.
then go back in time, essentially say it had to be much more than it is, you know. So Hubble saw how there was a red shift and a blue shift, I believe, in the galaxies or
Yes.
stars, and that's how he knew that they were moving away from us
Yep.
or moving towards us.
That's right.
And this is analogous to people who may not understand that. It's like when you're driving and you see a car, you hear a car going, "Yeah."
Exactly.
So if it's moving towards you, it sounds
Yeah.
higher pitch.
That's right.
As soon as it's moving away, it's lower pitch.
That's right. Yeah.
So light, similarly, if it's moving towards you, it's going to move towards the blue spectrum.
That's right.
If it's moving away, it's going to move towards the red part of the
Yep.
spectrum. Now, if we're in space,
Yep.
how could we know that if we're here? I mean, we don't have another location in space where we can actually compare
Yep.
the direction of if that makes sense. I mean, if we're looking at it and we're seeing blue,
Yep.
how do we know it's just not blue versus it's a different color and it's shifted to blue? If that makes sense.
I'm not sure that I understood your question.
So
Sorry.
when you're driving and there's
Yep.
a car going past you, that car actually goes past you.
Oh,
To
okay.
his shift.
Right,
My
right,
question is, how do you know that about galaxies and stars?
Okay. Well, because what we're looking at is this is where we know what the spectrum of elements are in the lab environment, so they're not moving. So we know, for example, emission spectra or absorption spectra, we know where those lines should be. But when we get them from, for example, a star, those emission lines or those absorption lines from a gas that they've gone through on the way to us, we'll see that those lines aren't in exactly the same place we expect them to be. So those lines, either all of them are shifted towards the red or all of them shifted towards the blue, because that it's not just one line you're looking at all of the lines, and if you've got your template from what you know in the lab, then you can work out, that's such and such an element, but it is shifted, it's shifted either to the red end of the spectrum or shifted to the blue end of the spectrum. So it doesn't have to actually come past us to know that it's like you're hearing a particular tone and a whistle, for example, but it's not the pitch you expect it to be, because in the lab that the whistle is a particular pitch,
Right.
and if you're hearing it and it's a higher pitch, it must be moving towards you,
Right.
and if it's a lower pitch, it must be moving away. But you don't have to have that change in pitch you just have to know
The original pitch.
The original pitch, yeah,
That is,
or the lab, the pitch in where it's not moving. Yeah.
okay, that makes total sense. That's interesting because, I hadn't even considered that, because each element would have their own bands along the spectrum.
It's got its own fingerprint, as it were. Yeah.
Yeah, so along the light spectrum, you see these dark bands.
Yeah, that's an absorption spectrum. Yep.
So those bands don't necessarily. So they might move.
Their spacing won't change.
but
Yeah.
they'll move
Yeah.
collectively.
Yeah.
Left or
Left
right.
or right, yeah.
And that's how you know.
Yes.
Okay.
Yeah.
That answers my question.
Yeah.
That's okay, that's
Good.
cool. One other question that I think I tried to look for it in Google, and so we're orbiting the sun.
Yep.
So shouldn't we be seeing a different part of the sky as we're orbiting the sun? And do we see that?
Yeah, definitely. Yes. Yes. So I mean, if you were to go and look at the night sky every week for a year, you'd notice that you'll see different constellations up in the sky, and that's because we are moving around. So we see different constellations at different times of the year. We'll see some that we see most of the time around the year, but they're the ones that are around the south because they're always in the same sort of point in the sky. But others, they'll come and go throughout the year.
So the ones that are towards the north and the south, they remain pretty much regular.
Yeah.
Because they're in this part of the universe.
Yeah.
And everything around here.
That's right.
Towards the equator.
Absolutely right.
Won't be seen.
It won't. Well, we'll see it
Will
at
be
certain
changed.
times, but it'll change throughout the year. That's right.
Oh,
Yeah.
that's so cool.
Yeah.
Okay. We still have about 10 more minutes.
Okay.
I was wondering, are you being an astronomer, do you contemplate asteroidal impacts? Does
it keep me awake? No. No, but it won't surprise me if it happens. Yeah, because these things have happened in historical time and are bound to happen again. So there've been plenty of near misses, and I'm sure it will happen at some other stage. Whether we'll know about it ahead of time is a different matter. There are some groups in the Northern Hemisphere who are observing and searching for that. I'm not sure if we're doing it in the South. There was a group, I think from ANU, that used to do this, but whether they're still doing it, I don't know. Yeah. Do
you think it's an important thing to research to find ways to ensure that humanity isn't wiped out like the dinosaurs? Do you think that's possible?
Is it possible? It all depends on the size of the thing that's going to hit us, and I'm sure that there could be some strategies developed to minimise that. I mean, one thing you wouldn't want to do is blow the thing up, because all you're doing is making more pieces to hit us.
Right.
But to be able to deflect it, I'm sure that if we needed to, we could do something like that.
Okay, that's something that actually I think maybe I shouldn't spend too much time thinking about it, but it freaks me out.
There's not much we can do about it unless we all get together. The whole world gets together basically and says this is important, and we need to develop a strategy.
Right.
But I guess it also depends on the probability of it happening. Now it will happen at some stage, but I haven't looked at the exact stats or the probabilities of that. There are people who actually study that, and they'd be able to get a much better answer than I can.
The reason is because there are certain things that happen, let's say every 10 years, and we can plan for it. As humans, we see the urgency of it, but as soon as it hits, it's outside of our lifespan, something like 1,000 years or 10,000 years or 50,000 years, no one wants to deal with it.
No, but also humans are terrible at assessing risks, and not scientists, that we're pretty good, but we understand maths and so on. But the general public, at assessing risk and what is really dangerous. I mean, we're especially in Australia, morbidly scared of nuclear energy. But there are things that are much riskier than that, because we can't assess those risks. That it's this thing we can't see, and we sort of have a fear of it and so on.
Right.
But there are the risks are disproportionately associated by people.
Right, and it's sometimes beyond our comprehension.
Yeah,
like you said, we don't have the statistical tools built in our brain.
No.
You will see and that's the thing. We're so built to see patterns.
Yep.
And if those patterns aren't close enough to each other, then we don't see them at all.
No.
So, So after your PhD, what did you get up to?
Well, as I said, running this observatory.
Mm-hmm.
Yeah. So I finished my PhD in 2015. So yes.
Oh wow! So it's recent.
Very recent.
Wow.
Yes.
So
as I said, I started in 2007 doing it part time. And finished in 2014. Graduated in 2015.
So you were teaching as well
yes.
as researching.
Yes.
We're reaching towards the end, and I think I have 3 more questions, and I'll let you go. I appreciate your time, Ain. Where do you see your field going in, let's say, 50 or so years?
Well, that all depends on what instruments we can get built. So if the Square Kilometre Array ever gets built...
What's that?
Will be the biggest radio telescope ever built. So it's a project that will build thousands of radio telescopes here in Australia and in South Africa, spread across the world, and effectively make the biggest radio telescope ever.
Why is it spread across the world? Could you explain that?
Well, because with radio telescopes, or like any telescope, the collecting area, the bigger the collecting area, the more sensitive the instrument is, the more sensitive, the further back you can see, and but making just one single dish that size is impossible. So you make it out of lots of smaller telescopes, and you spread it out over a big area, and effectively that's how, like, having one ginormous telescope.
I see. And does are radio waves obviously larger waves than let's say what we see in light? Does that also have something to do with the spacing out of those?
No, because you can do the same sort of things with optical telescopes, but you don't get the same advantage. So also when you're looking further back in time, as it were, things are shifted. Once again, this is shifted down to the lower frequencies, so they get shifted down to the microwave, the radio frequencies. This is why we have the microwave background. Okay, so because it's far back in time, it's all been shifted towards the red end of the spectrum, or shifted down to the radio, to the microwave frequencies.
Right, okay. That makes sense. Before we get into the last two questions, I do want to ask you, this is something that I've looked at in different documentaries, but it wasn't quite clear. You also mentioned the microwave radiation background, right? Yeah. And that is a signature of the Big Bang.
Big Bang, yeah.
And you said looking back in time. So when you point your telescopes, can you point it anywhere and see that signature, or is there a specific area in the universe?
Everywhere. You see it everywhere. It's everywhere. And it's everywhere because because the universe is everywhere, and this is where it's really tricky, even for me, to wrap my head around, because we always think of the Big Bang. Okay, there was nothing, there was this thing, then there was the bang, and it expanded. And what's it expanding into? Well, that's the thing. There was nothing. It's creating space and time as is expanding. So where is the center? Everywhere is the center, basically. So that microwave background radiation is everywhere.
Right, because it's expanding at every point in space.
Yeah, and creating spaces. So the Big Bang created space and time. So yeah, it's really hard to wrap your head around, and try and describe it is really difficult.
And so that microwave radiation, that tells us what?
Well, that's basically the afterglow of the Big Bang itself. So when the Big Bang occurred, that's the heat that the Big Bang created, but that heat has, as I said, been shifted down to, because it's so far away and so long ago, shifted down to the microwave frequencies.
Oh, so that also experiences a redshift.
Yes, yeah. Oh. So redshift is another way we can tell just how old something is. So the higher the redshift, it tends to be older because it's moved further away.
Right. Yeah. You said it's the afterglow. How long after the Big Bang?
It's only now you've got.
Is it like a second or a day?
No. I think it's it's in the first 300 milliseconds or something like that.
Oh wow.
Yeah.
And so why can't we detect anything before that?
Why can't we detect? Because of that glow, we can't see past that, basically. So that obstructs the view of anything before that.
So the radiation itself prevents scientists from looking.
Yes.
Before.
Yeah.
Why? How does it do that?
Well, because it's like you're being somebody's shining a flashlight in your eye and you can't see past it. Yeah.
Okay, it's like, imagine you had your high beams on a dark night, and you're standing behind a car or something, and I'm trying to look at you, but the high beams are blaring right into my eyes, and I can't see before that. Yep. Okay, that's interesting. Wow. Okay, last two questions, and so one question, the first question I'd like to ask is, what are you most afraid of when you're looking to the future? And this can be in whatever context.
Oh, what am I most afraid of? human stupidity. Yeah,
how so?
greed. That's unfortunately things I've got no control over. Apart from my own decisions and so on. What we do as a world. Or as governments. I think that's what scares me the most. Yeah, I mean our response to global warming and all of those things. Turning away from science. That's what scares me.
And that's been happening.
Yes,
more and more, I think.
Yeah.
And I was watching a documentary. I think it was Richard Dawkins, and he was talking about how people think that the opinion of an ordinary person is just as valid as the opinion of an expert who spent 20-30 years researching something.
Yes.
And that's concerning. And he was saying that this is similar to the Protestant movement in 1500s, 1600s, when Martin Luther translated the Bible, and then everybody had access to it, and everybody had their own interpretation of the Bible, and then no one respected experts at all. And I think a similar thing is happening, and that's really concerning.
Yeah, I mean, everybody's entitled to an opinion, but opinions have different weight. Yes, an expert's opinion should be much more valuable than somebody who has not done any work in that particular field. So yes, everybody's entitled to their opinion, but as I said, opinions have different weight.
Yeah, the very last question, which is the flip side of that. What are you most hopeful or about when you're looking to the future?
I guess the flip side of what I've just said, that the human condition can actually rise above that greed and that stupidity, and hopefully it will, and it'll come to its senses and realise we're all human beings on this very, very delicately balanced spaceship orbiting the sun, and that we need to actually pull together rather than rip each other apart.
I agree with you completely. Thank you so much for your time, Ain.
It's okay.
This was very informative, and I had a lot of fun talking to you.
Okay, great. Thanks.
Thank you. All right, guys, let's get this party rolling.
Yeah.
So how should we start this podcast, dude?
Well, I like how Ain says he's studying the biggest explosions in the universe. When he did his honours. He had
supernovas?
Yeah. He loved exploding stuff, so he went and studied the biggest explosions in the universe.
Dude, I thought that was funny. And then I go to him, I'd get arrested. He goes, yeah, we'd all get arrested. I'm like, no. I was thinking in my head, I'd get specially arrested.
Yeah.
Looking like me, they were like, this terrorist, he's making an explosive fertilizer bomb to blow up some tower in the city. So yeah. But
yeah. Sorry, I thought you were halfway through a sentence.
No, I wasn't.
Then I looked up and you were looking at me, and I'm like, oh shit, you want me to say something?
I was expecting some eye contact.
Yeah. He was. It was very appropriate because he's talking about sharing, like how being the astronomer in charge at the Western Sydney Observatory, that he gets to share a lot of his science with kids. I thought that was cool. And actually, I forgot to bring it in for you.
What?
Let me tell the story, and then you'll know what I forgot to bring in for you.
Okay.
Yesterday, I bought some red cabbage. So, for people who don't know, red cabbage is like a pH indicator. So you can use it, and it changes different colours.
What is pH?
I'm not doing that now.
Come on, pH is
Sunday
just
morning, man.
How acidic or how basic something is. How acidic or alkaline something.
Yeah.
Just in case, dude.
All right. So anyway, basically, I'll tell that in the story. So basically, you boil red cabbage, right? Mm-hmm. And it has this really, really like purple, like insane purple kind of color water you get out of it. You just let it cool down, and that water, that purple water, is actually a pH indicator. So it tells you, it changes color if something is acidic or if it changes color if something's basic. And because it's just cabbage juice, it's like totally safe. so you can use it with kids, and like the colors it changes are like, you know, hot pink, you know, yeah,
Really?
yeah. Like they're the types of colors. It's
Oh,
not like
shit.
it's not like a subtle change. You go in like acid. It changes from purple to red with acid, and then it goes even more pink and like hot pink, like really, really hot pink. Something you'd see at like the Mardi Gras or something, like seriously, yeah, like full on hot pink with really acidic. So that's that side. But then the other side, it goes from purple to like a bluey color to green, and then to yellow to really basic. So it's cool. So you can make this stuff with kids, and this is what I forgot. Actually, aliquoted out, like made heaps of different vials of it, and I was going to bring some in for you to share, like to give to your
I have nieces.
yeah,
dude.
your nieces or nephew or whatever, and
Dude.
and you can go and test stuff, because I was testing stuff with the kids. It's great, you know, like
Yeah,
and you get them to predict what color it's going to change. So you know, you do something like lemon juice first, and you get them to taste the lemon juice, and they go, oh, it's sour, you know, and you get them to predict what color, and they get all these wild colors, and then it goes pink because it's an acid, right? And then you do something else, and you get them to do like vinegar, and you get them to taste the vinegar, and they go, oh, that's kind of like sour, like lemons, you know. And then you get them to predict what its color it's going to go again.
Yeah.
And then you can and then you get bleach, but you don't get them to taste the bleach.
Oh,
You put a tiny little drop of that
on their tongue,
and then it goes. No, I just use a shot glass, but I don't shot it after. Yeah, and then you put it in there, and it goes like. Well, this was actually interesting. It went green first, and then it went really yellow.
Really?
So I think maybe it was just taking a bit of time to mix up in the solution
Yeah.
or something. But that was cool.
That's really fascinating.
Yeah.
dude. So you're putting those solutions into the pH indicator.
Yeah, well, you can
Or
mix it.
what?
You can mix it any way you want. You're just going to mix it together. Like the bleach, you only put like a tiny drop of bleach in the bottom of like
Yeah.
a shot glass or something, and then you just pour the indicator on it, and the indicator goes from purple to like bright yellow or bright green.
Oh, that is so cool,
But
man.
the color change, you got to see it to believe it. It's not like subtle at all. It's like you know, it's more green. It's more green than that. It's more pink than that. It's like hot pink. Like that's the type of colors we're talking. It's crazy.
Dude, that's a really cool experiment I have to do with my nieces and nephew.
Yeah.
Yesterday I did some experiments with them about density.
Yeah.
So what I got was I had one cup filled with water, another cup filled with oil, and I
Yeah.
got them to predict what will happen, what's going to go on top, what's going to go
nice.
on the bottom, right?
Yeah.
And they're like, oh, what a couple of them were saying that the oil's going to go to the top, and the other one was saying the oil's going to go to the bottom.
Yeah.
Like, let's check it out. And then they mixed it, and they saw, oh, there are these two distinct layers.
Yeah.
Before that thing, I asked them, will it mix? And they're like, oh, no, it's not going to mix. And my niece is like, yeah, it will mix.
Yeah.
And then they found out, oh, it doesn't mix. And then
Yeah.
they're like, oh, why is the oil on top? I'm like, that's a really good question.
Yeah,
You
yeah.
know what I mean? And then we talked about, like, I didn't use the word density. I just talked about which one do you think is heavier or lighter?
Yeah.
Do you know? And they're like,
Yeah,
oh, the
yeah.
oil is obviously lighter because it's
Yeah.
on top, you know? And we even, my little niece is like, oh, what if you, like, do you turn the cup around like this? Oops. You turn the cup around like that. What would happen to
Yeah.
it? And I go, that's a really good question. And she's like, I think the water's going to stay on top if we do that.
Oh, yeah.
You know what I
Yeah,
mean?
cool.
Yeah.
And you did it?
And my nephew's like, no, I think oil's going to be on top. And we did it, and the
Yeah.
oil stayed on top. They're like, why is that happening?
Yeah. That's cool.
You know, then I asked them, I go, what about air?
Yeah.
Is air heavier than water?
Yeah.
They're like, oh, I don't know. And I'm like, how could we test it? And my little niece is thinking. She goes, what if we get a straw and we blow into the water?
Oh, good idea.
I'm like, that's a really good idea. And
Yeah.
it's actually amazing
Yeah.
when you get them thinking about stuff
Did
like
you try food dye in there as well?
We didn't have any food
Oh,
dye.
yeah. You got to go and do next time you see him, do the same experiment, but you put food dye, and we both know how it's going to turn out. The food dye dissolves in water, but it doesn't dissolve in oil. So the oil's on the top, and the food dye will be a really solid, perfectly round droplet in the oil, and it will slowly sink through the oil, and then it hits the water and goes bang and instantly dissolves.
Oh.
Yeah.
And we should do it with like warm water and cold water.
Yeah,
That'd be
yeah.
interesting.
Warm water and cold water is another good one, because the cold water, the temperature is a measure of how quickly the particles are moving, right?
Yeah.
So if the water's really hot, the particles are moving really fast, and when you drop the colouring into it, it disperses through the liquid really quickly. But if you put the water in the freezer until it's just about to like freeze and take it out, and you drop the water in that, the particles are moving so slowly that the droplet of dye just stays in there, and it can take like tens of minutes, a long time to disperse through the water.
That's really cool.
Yeah.
I think that it's very important to do that with kids.
Well, they're naturally curious. Like they love that type of stuff because they just like, it blows their mind just thinking about why that would be. And yeah, it's cool.
Yeah. And if you feed that curiosity, I mean, it's so important. Like when I was growing up, I never had people do experiments with me, but I was just doing little experiments by myself. Like when I used to live in Pakistan, I was about 5-6 years old. And you know how you have like those drain pipes that come from the roof? Yeah? It was made out of copper. I don't know what it was made out of. But for some reason, I don't even know what caused it, but it would get a buildup of static electricity. And this would happen on like hot days, I think. It was really weird. And when I would go and touch it, it would shock me. And I would remember, why is this happening?
Yeah.
Like, this is so weird. What's causing this? Is it the sun? Is it what's causing this? And I remember like being so just I don't know. I was just like, what the hell is going on? And I don't know if I told you the story, but we had like in Pakistan that they didn't have like the same sort of rules and regulations when it comes to constructing new buildings and houses. I don't know how, but they had like pieces of sodium, dude.
Yeah,
like
geez.
Pieces of sodium.
Yeah.
And how I knew later on this was sodium was we actually did an experiment in class where they put like a solid block of sodium in water.
Yeah.
And sodium, for the guys who don't know, as a metal is very reactive. It's very unstable. It can react with water really quickly to produce hydrogen gas, I believe, right?
Don't ask me the details.
No, it does, because I think sodium reacts with the OH of the water, so H2O, so the OH and produces sodium hydroxide, and the hydrogen. I'm not even going to comment on this, but anyway, it produces hydrogen gas, and that heat. It's an exothermic reaction, meaning that heat is created from that reaction. The heat and the hydrogen gas. You have heat plus fuel plus oxygen.
Yeah.
You can use that to cause explosions. But what I'll do is like these tiny bits of sodium, like these pebbles almost. And Muslims, they before they pray, they have to do this ritual where they have to clean themselves, their face, their arms, and their feet. And when they go pray, usually, parts of their body are still wet. And what I'll do is I'll throw a bit of that sodium pebble I'll put on people's feet while they're all praying, bro. It'll start to dissolve.
Shit.
Also, you know what I mean? Give it to people when they had wet hands.
Yeah.
It's so messed up. I thought, dude,
no respect.
No, I was just curious. I'm like, okay, well, clearly,
Just curious.
yeah. Okay, maybe. No, I'd never thought about the respect thing. I was just like, why does this happen? Why does it, first of all, boil, and why does it hurt people? You know what I mean? And how many people? I just needed to just confirm that it did hurt people. So I just needed some more some more trials, some repetitions to ensure that my data was actually meaningful. But it was really cool.
What struck me, we should get back to Ain. What struck me is, because you and me are both in like biophysics, and I like how, like a lot of people I think have this view of science that everything's really distinct, biology, physics and chemistry, but they're not. Like techniques in one kind of pass over to the other, and where Ain's using Fourier Transformation to kind of, look at stars and things like this, and to analyze the data that he's getting back.
Look at the stardust.
The spectrum, and we're doing the same thing, but in cells. Yeah, so it's interesting. It's the exact same technique, but transferring one from the cosmos, the biggest things that we can see, to stuff that's microscopic.
Tiny, and it's really cool because as a kid I was always fascinated. I shouldn't say as a kid. I think as I finished high school, I watched more like physics documentaries, and then I really started to appreciate how cool physics was.
Yeah.
You know, as I told Ain, the math kind of turned me off, but the philosophical aspects of physics, you know, where we describe nature and how it works in terms of just words, that fascinates me. You know, but
I think it's really interesting because there's a lot of like famous physicists as well, and this is like, you know, every time I listen to physicists get interviewed, people just like throw all these questions they have about, and it was the same when you were talking to Ain. And I'm like, oh, poor guy, these guys must like just get bombarded. But it's because this stuff's so interesting and it's so like different from us. Like people kind of have an idea about how humans work and how life works because, you know, that's what we are, right? But like when you're talking about supernova, it's just, you know, it's so far removed. When you get somebody who spends their life studying it, you just want to like grab every piece of knowledge you can from them. Yeah.
No, for sure. And supernovas are, you know, physics in general, I think, is so out of human. It's not within the realm of human intuition.
Yeah.
You know, like what you would intuitively think is the case is not the case. And Neil deGrasse Tyson puts this beautifully. You know, the universe has no obligation to make sense to you.
Yeah, and I think in a lot of physics stuff, it doesn't make sense because it is so far removed, you know?
It is so trippy.
Where we can kind of get things in biology like evolution and stuff like that because it makes sense to us because we're living it, we're feeling it every day. But this stuff's so removed from us, you really got to think in a different way.
Yeah, especially when you get into like astrophysics. Like I've heard Neil deGrasse Tyson, even Lawrence Krauss, when they talk about like something like supersymmetry, my brain just starts hurting. I'm like, what? Yeah. Like, how? What? Like, I have like no way of comprehending what the hell they're talking about. And this goes back to my discussion with friends, you know. Someone like Ain who spent years and years and years researching, you know, working in the field of physics, in astronomy, I should say. Like, my opinion is jack shit compared to him because I don't know anything, and I've heard people like make this claim, and this is in do you remember that global warming lecture that or talk that we were part of as well, and he was saying that, you know, people spend 20-30 years of their lives researching something and dedicating themselves to finding as much as they can, find out as much information as they can, reliable information, and along comes some jackass with an opinion, and everybody pretends like those two, like the expert opinion and the jackass opinion are tantamount,
have equal weight. Yeah,
exactly,
but they don't.
It's so
That's right.
it's so,
and like sure, and you can always like the argument to that is, oh, but experts can be wrong too. Which is like, sure, they can be, but I know who I'm betting on. You know what I mean? You know what I mean? Like, if I had to take my pick on who was right, I know who I'd be going with. I'd be going with the guy who spent his lifetime researching it. Now, sure, I could be wrong.
Yeah,
that might not be the right decision, but hey, it's probably the most wise one.
But you can mitigate even your chances of being wrong by consulting many experts. You know, if you're just putting all your eggs on the same one basket of this person's opinion, then
talk to a different expert. Exactly.
There's a guy that Joe Rogan had. He had made some, you know, a lot of headway in the field of cancer and cell biology. Just a fascinating dude. Peter Duesberg, I think his name is. But he's this wacky dude who believes that AIDS or HIV, the virus itself, is not what causes AIDS.
Oh yeah, the guy who invented PCR.
Yes.
Muller.
Something like that.
Yeah.
Something like that.
He that's who you were talking about.
I think it's the same guy. Peter Duesberg. I'm not sure.
No, it's not Duesberg. It's something else. I'll probably look it up. Carrie Muller or something like that. But the guy who invented the PCR reaction, he also is pretty crazy. He believes in an AIDS denialism and things like this, and I think he believes in aliens and stuff like that.
Yeah, he's a professor of biology at California. Let's see. I think this guy...
Molecular biologist. No, he's a molecular biologist too, but it looks like a different...
Duesberg on AIDS. What causes AIDS? Yeah, this...
Different guy from the guy.
Yeah.
But anyway, yeah.
But the point I'm making is that, like, if you just listen to that dude, even though he's made some great headway in other parts...
Yeah.
That
doesn't discount his other things just because he's a whack job.
Yeah.
It's the same, like the PCR reaction still works, right?
Yeah.
Just because the guy invented it was Fruit Loop
Yeah.
doesn't mean that the technology itself is
It's
bugged.
not.
Yeah,
Just
exactly.
like, I think Darwin had some wacky ideas as well, besides evolution, right? But that doesn't mean that evolution, the theory itself, is nonsense.
Yeah,
And same.
well, yeah.
But the point I wanted to make here was Peter Duesberg. Again, if you consult this one dude, you're going to be convinced of his argument. But when you consider other arguments by other scientists who are, when you look at what the bulk of scientists are saying, that's who you want to go with, because the people who are on the fringe can be right. And you read that beautiful quote a couple of weeks back about Carl Sagan,
Bozo the clown,
about Bonzo. What's
Bozo.
Bozo the clown. Like they say that who and so got laughed at.
But we also laugh at clowns and idiots as well.
Yeah. So you have to be careful that some people may, and that's the thing. If I'm not an expert in the field, I'm too dumb to know if someone is wrong.
Yeah.
Do you know what I mean?
Yeah.
And so you have to recognize that.
That's where critical thinking comes in, I think,
and just recognize that. But can I just go back to the biophysics aspect of it? So Alex and I both, so we were talking about like red shift and blue shift in that episode, right? So if a galaxy is moving away from us, it's going to be a red shift, right? If it's moving towards us, it's going to be a blue shift. And all of these, if you look at the light spectrum, the colors from blue all the way to red, what you see is certain molecules, and this is how we know what the sun, for instance, is made out of, right? What you do is you let the light go through a prism and it separates the colors, and then you see these dark bands. They're like a barcode, like a fingerprint.
Where the molecules are absorbing light.
Yeah.
You see these dark bands where the light isn't. Yeah.
Yeah, exactly. It's being absorbed, and those dark bands, those are specific to specific elements in.
They form like a fingerprint. The pattern of bands forms a fingerprint, and we can tell what they are.
Exactly, like helium would have a certain fingerprint, hydrogen would have a certain fingerprint, and so on and so forth, right? But what's cool is that fingerprint changes. Like you might have the same barcodes, but the colors might change towards the blue or the red part of the rainbow, depending on what's happening. If it's moving, there's a lot of factors that might go into it.
If it's standing still, it's in the middle. If it's moving away from us, it's red shifted. If it's moving towards us, it's blue shifted.
Yeah.
But the fingerprint's still there.
We use that, this red shift, blue shift, not in terms of movement, but in cell biology. So if we have a molecule that is fluorescing, meaning that it gives off light, we could actually use that to attach it to certain molecules inside the cell that we can then get an understanding of the environment. So it would experience those shifts left or right depending on what's happening around it.
Yeah.
So for instance, if the DNA, which is like the genetic code of the cell, if that's being read, certain machines are being made, it will shift in a certain way. If other machines are being made, it will shift in a different way.
Yeah, and part of, actually, it's right on my thesis topic. So part of the shifts I've seen in the dye that I'm using to stain stills, it like red shifts it by 8 nanometers and things like this. It's slightly different because we're talking about the light that's emitted off a fluorophore, where they're talking about the light that's absorbed by a molecule. But it's the same type of idea.
Same sort of concept.
Yeah, exactly.
But again, like that's so cool that the models of the universe that we have in terms of how big it is, how the galaxy or how the universe is expanding, all these things that physicists have established work.
Yeah.
Right? And they work so much that we can take those concepts
from one field
and apply it to biology, which is our field. And I was talking to my friend, and he's like, how do you know that the earth isn't flat? Because he has friends who are flat earthers, right? And I said, dude, the amount of evidence that's there to suggest that the earth is not flat is astounding. This is one example, right?
Yeah, I think it's about, so the evidence that would suggest the earth is flat works in the same respect that this evidence does, right? So we know that this is true, this shift, because it works in physics, it works in biology, it works whenever we use it, it works. Doesn't matter what, you can take it out of into a different context, it still works. And it's the same that can be said for the evidence of around Earth. I almost said evidence for a flat Earth.
You did say flat Earth. Well, like, what is he on about?
Flat
Earthers are going to lose their shit and say, shit.
That evidence works in other contexts. So if it was false, it wouldn't work in other contexts, and then we could say, well, it's wrong. But it doesn't. It does work in other contexts, so it's okay.
Exactly right. So if the Earth was flat, then it'd be the physics would be so off, because then you wouldn't be able to explain how gravity works. Why? It just doesn't make sense. So the whole model of the universe that we would have would fall apart. The physics that you and I work with wouldn't make sense if the Earth was flat.
Yeah.
And this is one of the reasons why I do believe, based on evidence, that the Earth is round. And for the guys who aren't convinced, just like, for God's sake, just think about...
How many of them listen to this podcast?
I don't know, I hope a lot. No, but the problem is everyone's trying to look for things to confirm their theory, or I shouldn't even say theory, their hypothesis, because that's the correct term to use. But no one's trying to disprove it, and that's the problem.
We can't let this little post chat go without discussing aliens, man, because I've got a very interesting point. I thought when Ain was talking about, he was talking about not wanting to make anthropocentric assumptions about aliens. I think you asked him some question about the motivations of aliens and how we shouldn't. Then he goes, I don't like making assumptions and putting the assumptions we have about our lives onto that of like what aliens would be. Mm-hmm. And in one hand, I kind of like respect that idea because it's kind of right. But on the other hand, I was kind of thinking, but you have to do that to some extent to actually go and search for ET, because Ain's work, when he was looking for ET, he's like searching for signals that people would send in radio waves, right? That is an assumption that an alien species would want to communicate to us in radio waves, which is something we don't even really do, I don't think, anymore. I don't think we're putting out any signals in radio waves or anything like that. So
we might be, aren't we?
Oh, we'll incidentally, but I don't think we're putting out any signals that say, hey, aliens, come find us and stuff like that.
Right. I think that, but just going back to the radio waves, I think I was reading something on Facebook. There was like, I fucking love science, that Facebook page that they have. They were talking about radio waves, short or narrow range radio waves, like this broad and narrow. They were detected from a red dwarf. So when I was talking to him, I said this is potentially, it could potentially be an alien. He's like, potentially is the key word.
That's right. Yeah, because how do you tell the difference between that and some natural or some other natural thing you don't know about? But even that is an assumption. So he was saying he didn't want to make assumptions about that, but you kind of almost have to make assumptions to go and look. And so you have to make the assumption that these aliens would want to transmit or have radio waves. But even it also goes to astrobiology, right? So people who try and look for alien life like microbes and things on other planets. You just have to make an assumption that life on another planet is the same as life here, or similar to life here, or has some aspects to life here. So what they say when they're looking for isn't, when they say they're looking for life, what they're really saying is we're looking for life kind of like us, because that's how we're defining it. So it's kind of like this catch-22. You don't want to make assumptions, because if you make assumptions you might miss something, and you don't want to miss something. As a scientist, you want to go in and just look at what you're presented with, but it's almost a catch-22, because in order to actually look, you have to make some assumptions, because otherwise what are you looking for? Right. It's interesting.
It's interesting because it's a good point, but I think I pointed this out to Ain as well. I heard this on a podcast. It was on one of those NPR podcasts about a certain scientist, or I don't know who it was, but he was saying that if there was life on another planet, obviously they would need 2 legs to walk. They need a mouth to talk. They need to defecate and get rid of. So he essentially came to the conclusion that there's another human civilization on another planet. Based on his assumption. And I brought up The Expanse as a TV show for Ain. They did a shit job of explaining what the proto-molecule was. So the premise is this, that this is hundreds of years after like hundreds of years from now, we've developed Epstein drive, which is these nuclear reactor jets, essentially, that can...
Sounds like you're describing the plot of Mass Effect here, but keep going.
Dude, it's actually really
it sounds like
it's so cool.
This is the setup for the Mass Effect plot. 100 years in the future, humans developed this drive, found some stuff on it. You can keep going.
They can go between different, they can go, in the solar system, they can travel really fastly. But what's happened is that people have moved into Mars, and they want to colonize Mars and terraform it, and others have moved all the way to where the asteroid belts are to harvest water. To get... So they call them the belters because they lived in the asteroid belts. And then you have the Martians and the Earthlings, right? But the Mars and Earth are fighting over resources that they're acquiring from the belt system. So you have like these two superpowers who are screwing over like a third world nation. It's like, it's very analogous, right? Like cool. That. But what happens is that this proto-molecule, think of it like a contagion, comes from outside of our solar system, and these human beings find it, and they realize what this proto-molecule can do is transform life. So it will kill you, right? But it'll take all your memories, your life essence, and somehow transform that. Use your experience, your knowledge, everything like that, right? You're dead. But what it can also do is start to manipulate the laws of physics. So it can accelerate in this way, let's say at like 5 kilometers per second, then all of a sudden change trajectory and go the other way without anyone on that rock, like it's taken over a certain rock, without anyone feeling any G-force difference. So it's a really mind-blowing TV show, because it's not your typical aliens, right? It's this alien life form that can transcend time, because once it finds life, it can take over that life and then express itself and come to life. But until that time, it stays in a dormant state, and it can survive.
Sounds cool.
Which
might
is
have
really,
to check it out.
Dude, it's so mind-blowing. But it just shows like that's totally possible. It may totally be possible that alien life is so foreign to what we think is possible that it could literally manipulate the laws of physics that exist in this universe. That's totally possible. Is it probable? I don't know. But you have to be open to that.
Sounds very similar to the throw in a little bit of AI, and that's like the Mass Effect plot.
What do you mean?
Mass Effect plot is the Mass Effect trilogy, the video game. You throw in a little bit of artificial intelligence into that mix, and it's kind of like that.
Really?
Yeah, it's very similar.
It's such a good...
Similar in a sense.
Dude, it's so good. And I mentioned to...
I'm not going to explain any more than that, because I want Hamid to play Mass Effect, and if I explain any more than that, it'll be two spoilers. I'll be like giving away like the end of the last trilogy and stuff. And like,
I've given Alex and I have made a deal. Once he finishes his thesis, Alex is going to watch the 7 seasons of Game of Thrones, and in return, I'll play the the Mass Effect trilogy game. So I'm looking forward to it.
Yeah, it'll be good. I don't know. I think we should call it an end. We've been rabbiting on now for a long time. You got anything more you desperately want to say to the lovely people?
I guess I was really happy with this interview, because I had a bunch of astronomy and astrophysics questions.
You just unloaded on poor Ain. Tell me this. I have this really interesting question. I've always wanted to know this. Tell me, go.
Dude, I googled it. This is about the star stuff.
Yeah.
Because we live in the South Hemisphere, and we see this pretty much similar stars throughout the 365 days of the year. There's differences, right?
There's differences between southern and northern hemisphere.
For sure. Yeah, for sure. Because you're looking at different parts of the universe, right? And I remember, this is again, I think there's a positive to people who claim that the Earth is flat, because it gets you to realize why it's not flat. Right? You have to really check your understanding why.
Christopher Hitchens had this thing he used to say. I'm not even going to try and quote it, but he used to kind of say that the person who needs to hear a controversial is about freedom of speech, right? He said the person who needs to hear a controversial opinion the most is the person who disagrees with it.
Yeah.
You know, like, so like if you think a controversial opinion is wrong, then you need to hear it because it better prepares you to dismiss it.
Yeah.
You can call it out for what it is. Yeah.
So I was really happy. He kind of indulged me in those. It's like the last 10 minutes of the interview. It's like, all right, I have like 5 questions. I have to check. Okay,
Let me go through my list.
we went through the Big Bang, expanding universe, the microwave background.
Yeah.
How do supernovas work?
Yeah.
But yeah.
Cool. All right.
Anyway, have you seen any pictures of nebulas, by the way?
Yeah.
I had no idea that nebulas were the byproduct of a supernova.
Oh, didn't you? Yeah.
Or I shouldn't say supernova. I think
It's
supernovas.
gas. They're basically like massive gas, like huge though, gas clouds. Huge.
Yeah.
Yeah.
And they're so beautiful.
Yeah.
They're so beautiful.
Yeah. They don't look very beautiful through a telescope. You have to
Color enhance it.
take, like, they'll photograph for them for like hours at a time, and they'll take like little exposures. They'll take like hundreds of little exposures for short amounts of times, and they stack all the images on top of each other. And then some of the images are like high, a really, really high shutter speed, exposure time. So really long exposure time, so they get really dim light. And then some of them are really short exposure time, so they can resolve the really bright light. And they stack all these on top of each other, and they put them in, they color enhance it, and they bring out all the colors, and that's why they look so beautiful. But it's kind of like weird, like the color's really there, but to find it, you have to do all of this stuff because there's just so little light coming in from that.
Right.
Yeah.
But if you're on a spaceship and you're moving towards a nebula, you'd see it as you see it in the pictures.
No. Well, no, because once you're in a nebula, the gas is just around you, right? So you don't see anything.
You're in a spaceship, you're moving towards a nebula.
Why would you see it more?
No, I'm saying you would see the colors as it is, as we see it in the photographs.
No.
Or what would it be?
I think just the same.
Would it be invisible?
No, well, if you look at a nebula through a telescope,
No,
they kind of looks like, look.
You're in a spaceship, so the nebula is right in front of you, right?
Yeah.
I'm saying, but would you see it as you see it in the pictures that NASA has taken?
No, I don't think so. Because to see those pictures, you have to resolve them, and stack them.
Yeah, but you're so close.
Yeah, but when you're right in it, like nebulas are hundreds of thousands of light years.
Yeah, but you're far enough that it's close enough for you to see it. Do you know what I mean? Just like the sun is like as we can see it now, right? If you're that close to a nebula,
I don't know. I don't think it would make a difference.
Wouldn't you see those beautiful
colours? Because they're
colours?
so big, right? So like you have to be far away to see the whole thing.
That's what I'm saying, yeah. But not too far away.
Yeah, but if you, I don't know.
Just like the sun right now, right? We can see it.
Yeah, but it doesn't look different from a star, really. Like it's the same color as a star.
That's what I'm trying to get to. Would you, if you're that close to a nebula, would it look like what we see in the pictures, or has NASA altered those just like they faked the?
I don't think it would ever.
Satellite images?
I can't imagine it would ever look like it does in the pictures.
To hide the
when
fact
you're
that
when you're
Earth is
right
flat.
amongst it, you can't even see the thing at all because it's just gas really far away.
Yeah, but those colors, wouldn't you be able to see those?
No,
Why?
I don't think so. Because you need to be back far enough
That's
to get
what
the
I'm
whole
saying.
thing in the
If
picture.
you're back far
and when
enough-
you're back far enough, you can't resolve the.
Are you telling me that, like right now, right? If I'm like this, I can't see your whole body, right?
Yeah,
But
yeah.
if I can get this far, I can see your whole body.
But when you get
I'm
far
not-
away from a nebula, I don't think you get the color out of it.
Wait, you can't get far. That makes zero sense, bro.
Like, what do you? I don't know.
I'm saying, can't you get far enough where you get what the nebula looks like? Or
I don't think so. I think these things are way bigger and way further away.
Well, if they're bigger, bro, isn't there a distance that's sufficient that will enable you to see the nebula in your whole field of view?
I don't imagine so.
Oh my god, how does that make sense?
Maybe
bro?
like
How the hell does that
like
make sense?
like if you look at the Milky Way, like have you seen the Milky Way across the
Yeah.
night sky? I guess you can see a bit of color in that. So maybe there's
No, when you look at other galaxies, don't they have?
no. Well, if
they
you
have
look
colour?
at it, no, you can.
Don't they
like,
have colour?
Not really. No, they look like kind of like a bit blurry, I guess. Like almost grey kind of like but they're so faint, man.
So,
they're
I mean,
faint.
Look at our galaxy right now.
Yeah,
you see
because
there's-
we're right close to it. So
But
maybe
this color there, dude.
for the Milky Way,
Different stars have different colors. Different gases have different colors.
That's what I'm saying. So maybe there is a distance if you go like sit just outside it where you're looking up and all you can see is the nebula. But I don't know if that's
Why
necessarily.
wouldn't you be able to see that? That's ridiculous.
Maybe I don't know. Yeah,
This is why people believe in this flat earthers, bro.
because we don't have all the answers.
Yeah, bro.
Yeah.
Yeah. If you don't have the answers, then it's equally valid for me to say that my answer is correct, even though I have no evidence of it.
Yeah.
Don't you know that?
Not knowing is answer my evidence.
Yeah. What else could it be? That's a fallacy of ignorance, which I didn't even know was called a fallacy of ignorance. You could just say, man, just because you don't know something, does that mean that it's you can make a crazy assumption to?
Yeah.
Yeah.
That's
Anyway,
definitely a logical fallacy.
I think dude. I was watching that the show Matt Dillahunty's thing. It's so funny.
Oh, the Atheist Experience.
It's so hilarious, bro. It's so funny.
There's some really funny episodes. Some are a bit boring.
Some of them are so hilarious. Like
Some of them are great.
yeah, like people like call in, and it's hilarious because
They get prank callers too.
Do they?
You would have heard a few
haven't
prank.
seen
Oh
them.
yeah, yeah. They definitely get prank callers.
No.
Yeah.
I've seen people just lose their shit.
Yeah.
On the day, like scream. I'm like, dude, just don't call, man.
Yeah.
Like this guy, but he does get he gets super aggro. Like
Matt Dillahunty does.
yeah,
He gets a little bit aggressive.
He gets super
Yeah,
aggro,
yeah.
and I think
Not all the guests are like that
No.
though. Quite a few of them are pretty chill. Russell Glass is very, very good, I think, and Tracy Harris is pretty good.
Tracy Harris is I've seen her.
Yeah.
Huh.
I think Matt's really good logically, and he's quite a good thinker, and he explains things, I think, really well. But yeah, he's
savage, dude.
he's pretty savage.
He's
He
a
doesn't
savage.
hold any punches at all. You're an idiot. You're done. Goodbye.
Dude, that's the craziest shit ever.
Yeah.
But anyway, we've gone on too many tangents. This is 42 minutes. of
Yeah, I don't
recording.
know. Is it all going to make it in? We'll see.
we'll
Maybe.
just- If you guys have stayed this far, good on ya.
Yeah.
Anyway,
Catch ya.
wait, we have to talk about who we're going to have
No,
next.
we don't. We don't know who we're going to have on
We
next
don't.
week.
Oh, that's true.
Just stay tuned. It's a mystery.
It's a mystery. Yeah, anyway, thanks again for watching us and listening. Hope you guys enjoy it. Make sure you like our Facebook page, Instagram, Twitter, YouTube. These are video podcasts now, so you can get the video of this on YouTube. Check it out and share it with a friend. God damn it. And also, by the way, we're giving out free T-shirts, but it's a competition.
Well, they're not free. Yeah.
Yeah, let me just.
We
they're
expect
free.
you to work for us.
They're free in the sense that you don't have to pay for them. But what the competition is this: should we make it that you have to refer 5 people, or and then you go into the draw to win, or should we make it?
Well, if it's going to a draw, you got to refer 5 people.
Or should we make it the person who gets the most people to like our Facebook page and write, give so and so a shirt? That's the person who wins.
We could put everyone into a draw, and exceptional efforts get a shirt.
Fair enough. How about we do that?
Host discretion.
Yeah. No. How about we do that? Okay. One shirt is you go into the draw if you recommend 5 people, and another shirt is if you put a crazy, if you ungodly amount of people come to our Facebook page and recommend that you get a shirt, then if it's way more than everyone else's, then you get a shirt.
That's fair enough, I think.
Yeah.
Like good old Nathan did.
Yeah. If you got to put that, Nathan's our student. We teach him for a second year biochemistry class, and this guy, literally, what a gangster, man.
Yeah.
We said it just as a joke, initially, and that very day, he started hustling his friends. They're like, he got 8 people just. I'm fair enough. You deserve a shirt, dude.
Yeah.
Take a tingle.
Ciao.
Take a thing. That's it. Yeah. All right. See you guys later. Thanks for listening to Blab Codes. Rate and review our podcast on iTunes or wherever you get your podcast, because it does help us spread the word. And if you like what we're doing here, then help us grow it by sharing this with a friend of a friend, or your mailman, even your mailman's mailman.
We also want to hear from you, so send us questions or comments to blabquotes@gmail.com. And if you have any interesting questions or comments, then we'll talk about it on air.